Hello, and welcome to the Analysis of Variance ANOVA workshop brought to you by the Graduate Statistics Studio here at Fresno State. Today we'll be using the program SPSS to run an ANOVA. We will talk about three different ANOVAs today. This workshop will cover when to use an ANOVA, how to run the test, and how to interpret the output for the test. Before we begin, I want to talk about the data before you. We have 5 variables. We have group, class, score 1, score 2, and score 3. Group and class are both nominal categorical variables. Group has group A, group B, and group C, coded as 1, 2, and 3. If I click on this button here, it shows you 1, 2, and 3. Class is separated by 1 and 2, and is separated into the morning class or the afternoon class. Score is just a score. It's out of 50 total. The first ANOVA that I'm going to cover today is called the one-way ANOVA, sometimes known as the one-factor ANOVA. The one-way ANOVA takes one independent variable and compares 3 or more levels of that independent variable. If you have less than 3 levels of one independent variable, just use a t-test. To start the one-way ANOVA, we go to Analyze, Compare Means, One-Way ANOVA. Once we click on that, a new window appears. We have Dependent List and Factor. I want to move Group over to Factor and Score 1 over to the Dependent List. I can put more dependent variables in, such as Score 2 and Score 3, but for now I just want to focus on Score 1. The ANOVA by itself, unlike the t-test, will tell you if there is a significant difference, but it won't tell you how there is a difference. It will just tell you there's a difference in there somewhere. When you think about Group A versus Group B versus Group C, it's possible that there is a difference between Group A and Group B, but Group A is not different from Group C, and Group B is not different from Group C. So in order to make sure that we find which group is different, we use what's called a post hoc test. Click on post hoc, and we'll select Tukey. There are many here, and depending on which discipline you come from, you may use a different one, but Tukey is a really common one. I'll press continue. Next, I'll click on options. I'm choosing descriptive, just so that way I can see the means and standard deviations of my groups. I'll finish it off by pressing OK. And this new output appears, which gives me the one-factor ANOVA. The first table is our descriptive statistics. Here I can see Group A versus Group B versus Group C. There were 10 in Group A, 9 in Group B, and 11 in Group C. These are the number of people within that group. The mean for Group A was 5.8, the mean for Group B was 15.6, and the mean for Group C was 25.09. The standard deviations are right next to it. Below that table, we have our ANOVA. When we look at the between groups, we can see our sum of squares, our degrees of freedom, which is the number of groups minus 1, our mean square, our F statistic, and our significance value. This p-value, our significance value, is known as the p-value. If our p-value is at or below our alpha of 0.05, then that means we found significance. SPSS rounds up to the nearest third decimal place. So this isn't actually 0, 0, 0. We never have a p-value of 0. This is just a very small value rounded up. If I double-click on it and hover over it, see 1.9863e minus 14. What that's telling me is this is an exponent to the negative 14th power, so I would just want to move that decimal place 14 places to the left. So that means there are 13 zeros before this 1. It's a very small p-value, which tells us that there is a significant difference between Group A and Group B and Group C, but we don't know where that difference is. That is why we ran the post hoc to begin with. When I look down here, This is the post hoc test. We have the multiple comparisons table and we have the homogeneous subsets table. We'll first focus on the homogeneous subsets table. If we see there is a difference in these columns, and that is group A is in its own column, group B is in its own column, and group C is in its own column, that means there is a significant difference between those that are in their own column compared to those in a different one. Because they are in their separate columns, we see that there is a difference between the three. If, for example, group B was right here and group A was right here, and there was column 1 and column 2 had group 3 by itself, then that would tell us that group A and B are the same, or similar enough to be considered similar or different. Or they're similar enough to be considered the same, and group 3 or group C in its own column would be different from group A and group B. The multiple comparisons table is a little better to look at because you don't have to worry about looking at this. This is visually easy to tell the difference, but here we can actually tell the mean difference between groups. Here we have group A, which is I, and we can look at group B or group C. So the difference between group A and group B, or the difference between group A and group C. The mean difference shows us I minus J, so that's group A's mean minus group B's mean, which gives us negative 9.86. Here we have our significance value. Once again, this value isn't actually 0, it's just smaller. It's a very small value. So here we see there is a significant difference between group A and group B, and there's a significant difference between group A and group C. We can also go down to group B to see the final matchup of group B and group C, and there is a significant difference there as well. That tells us that every group was significantly different. When we scroll back up to the descriptives table, we can take a look at group A to group B to group C. If a high score meant something more positive, then that would tell us that group C had the higher score, meaning they had a more positive outcome. Group A had the smallest outcome. The next ANOVA I'm going to use is called a two-factor ANOVA or a two-way ANOVA. In order to use a two-factor ANOVA, we need at least two independent variables. Now that brings up an interesting point. The number at the beginning of an ANOVA is the number of independent variables that we will be using. A one-factor ANOVA, one independent variable. A two-factor ANOVA, two independent variables. A four-factor ANOVA, four independent variables. So the factor represents the number of independent variables. Or if we were still using the one-way ANOVA, that's still one independent variable, two-way ANOVA, two independent variables, and so on. In order to run a two-factor ANOVA, we need to go to Analyze, General Linear Model, and we'll click on Univariate. This window appears, and we have dependent variable and our fixed factors. Fixed factors we're going to bring over group and class. I'm then going to bring over score 1 for the dependent variable. Now what the ANOVA is going to do is it's going to take a look at score 1 across group and class. It will look at group by itself, it will look at class by itself, and then it will see if there is any interaction between the two. I'll explain an interaction momentarily. In the meantime, we need to run a post hoc test. Group is the only one that is going to be brought over. The reason for that is because a post hoc test can only be used when there are three or more levels of an independent variable. If we brought over a class, there would be an error. I'm selecting Tukey once more. Continue. Options. The options on the univariate ANOVA are different than the one-factor ANOVA, as you can see already. Descriptive statistics, estimates of effect size, it tells how strong the difference is between groups, and observed power. Power tells us how likely are you to find a significant difference if there actually is a difference. Continue. Finally, click on Plots. Plot will give you a visualized representation of the data. I like to put the independent variable with the most levels on the horizontal axis. That would be group. And for separate lines, I like to put the independent variable with the least number of levels. That would be class. Add this, and a line chart is fine. The reason I like to do group as the horizontal and class as the separate lines, and that is the most levels of the independent variable in the horizontal and the least levels of an independent variable as separate lines, is because we're going to see a line chart that will have different lines to represent the number of independent variables of the separate lines variable that we put in. It can get confusing if there are a lot of lines, so I like to put the least number of lines there, and the horizontal axis is easier to read than a ton of lines on the chart. Finally, press OK. The first table is a between subjects factor, group A, group B, and group C, which is group, and class. We have morning class and afternoon class. You'll notice that group has 1, 2, and 3, and class has 1 and 2. This is how the variables were coded, as I mentioned in the beginning of the video. Here we see Group A had 10, Group B had 9, and Group C had 11 participants. If we're just looking at class, morning class had 15, afternoon class had 15. Below that, we have the descriptive statistics table. Much like the one from before, we can see Group A and split it up in the morning class. We see 5.4, Group A afternoon class 6.2, and the total value. That is, if we combined both of these together, we would see the total value. If you wanted to look at just the class's mean difference, we go down to total, and we can see morning class 15.4, afternoon class 16.2. The total value is 15.83 if we just looked at class without looking at morning or afternoon. Our tested between subjects effects will tell us if there is a difference between the groups, if there was a difference between the classes, and if there was an interaction between them. First, we'll want to look at group. The corrected model and intercept, you'll never really have to worry about those. If we look at group, we see our degrees of freedom is 2, as before, so that's the number of groups minus 1. We see almost the same values that we saw in our one-factor ANOVA. Our p-value is still below 0.001, so it is a significant difference. Again, group is still significant. If we look at class, however, we see our F statistic is very low, and our p-value is 0.927. What that tells us is that there is no significant difference between class. That is to say that the mean in morning class versus the mean in the afternoon class are similar enough to each other that we would consider them the same. The difference we saw happened by chance. And if we go and look at our morning class mean, 15.46, versus our afternoon class mean, 16.2, we can see that those are really close together, not even a whole point difference. So that is why we don't see a significant difference in class. When I look at group star class, this is the interaction that I was talking about earlier. An interaction is looking at both independent variables together to see if there is a significant difference in one group if they also belong to another group. So did we see a difference in group, and did we see a different difference in group if we were looking at morning class group versus afternoon class group? The answer is no. We don't see a significant difference here. So this means there was a significant difference from group, which we would call a main effect in a two-factor ANOVA. There was no main effect of class, and there was no significant interaction between the two independent variables. Below we have the post hoc test. Here we have group A, B, and C, and again, they're all significantly different from each other. At the bottom, we see our estimated marginal means of score 1. We have our morning class and our afternoon class represented by a blue line and a red line respectively. Here on our x-axis, the horizontal axis, as it was called just a moment ago, we have group A, group B, and group C. These two lines represent the means of those two different classes for each level of the group. And notice how we see these lines are almost right on top of each other, which would explain again why we don't see a significant difference for class. The final ANOVA I'm going to run is the repeated measures ANOVA. The repeated measures ANOVA is like a paired samples t-test. It compares a pre-test to a post-test. The difference being a repeated measures ANOVA compares a pre-test to a mid-test to a post-test. There can be any number of mid-tests involved. That is, we can do 3 scores, or 5, or 100, although 100 isn't ideal. In order to run the repeated measures ANOVA, I'll click on Analyze, General Linear Model, Repeated Measures. The first window that appears wants us to name the within subject factor. It calls it factor 1 by default. I'm going to give it something more meaningful to what the variables were originally, scores. The number of levels, I have 3. As you can see here, 1, 2, and 3. I add the factor, I click Define, and a new window appears. Here we have the within subjects variables. I'm going to bring over score 1, score 2, and score 3. I now want to click on Options, Descriptive Statistics, Estimates of Effect Size, and Observed Power. Continue. Now I want to click on EM Means. Here, I'm going to bring over Scores, Compare Main Effects, and I'm going to select Bonferroni, which will adjust the confidence interval because we are measuring something more than one time. Continue. OK. Here is the output for the repeated measures ANOVA. The first table shows us which within subjects factors we used. We used scores 1, 2, and 3, score 1, score 2, and score 3. The descriptive statistics table tells us the mean of score 1, the mean of score 2, and the mean of score 3. Next is their standard deviation, followed by the number of participants within that variable. Because we only have one variable here, we don't need to worry about the multivariate tests. However, if you have more, you will see them displayed right below, and you'll want to focus on Wilks-Lambda. That is the most popular of these 4. Next, we have Maltese test of sphericity. Sphericity looks at the variance between the groups to see if they are different. We don't want significance here. However, we see a significance value of 0.015, which is below an alpha of 0.05, telling us that there is a significant difference. What that means is that the variance between our 3 scores are different, but that's not the end of the world. Once we scroll down to the test of within subjects factors, we have 4 options here: sphericity assumed, greenhouse geyser, Hjorn-Felt, and lower bound. We cannot use sphericity assumed because we violated the test of sphericity. Instead, we'll use greenhouse geyser, which is right here. We still see a significant difference, which tells us that there is a significant difference between our scores. That is, there's a significant difference between score 1, score 2, and score 3. But just like the regular ANOVA, we're not sure where that difference exists. We'll have to find the difference down here at the pairwise comparison table. Here we can see measure 1 for score 1, for score 2. So here's 1 to 2. There is a significant difference. 1 to 3, there's a significant difference, and 2 to 3, there is a significant difference. That tells us that there was a significant difference between all three scores. That is, 15 was significantly different from 26, was significantly different from 35. This has been an analysis of variance, ANOVA, and SPSS. Thank you for joining.